In this example, we're given a physical situation here, a physical problem involving 2-point charges. This is called a dipole. And these point charges are going to be located at these points which I've called C1 and C2. And their charges are going to be equal but opposite in magnitude. So Q at this point and negative Q at this point. And the distance between the centers of these two charges, that length is going to be lowercase d. So we're also told that we have a point P, which is in this case d units outside of the dipole, so capital D. We're also told that the electric field at P is given by this formula, so E is equal to Q over D squared, so inverse square law, minus Q over D plus lowercase d squared. So just the magnitude of the charge in plus or minus, right? So with its sign, the magnitude of the charge over the distance squared and then add them up. Okay, and so this could be rewritten as 1 over d squared, or even q over d squared, right? Times what? Times this is just going to be 1 minus 1 over, we took the q out, we took d squared out, so this is going to leave us with 1 plus d over d, so lowercase d over capital D. All here, lowercase d over capital D, quantity squared. And we're asked to show that this is about, so when P is far away from C1, when we get far away from the dipole, that this charge is about equal to, so it's proportional to 1 over d cubed. So sometimes we would write this as it's equal to big O of 1 over d cubed. And that's our goal here. So the whole job of what we're going to do is focus on this term right here and expand this out as a power series. So we're going to use a power series expansion of this term that has lowercase d over capital D, and we're going to work this out and see what happens to all the terms here. Okay, so that's our goal. Now, in terms of this function, what I would like to do is rewrite this as 1 plus lowercase d over capital D to the power negative 2, and this should make you think of a binomial series or a binomial function. So the next thing I'm going to do is just swap out this d over d, lowercase d over capital D, and just make it a u, and write this as 1 plus u quantity to the minus 2, and this is exactly a binomial, so we know exactly what to write down, right? So this is equal to the series, the sum of the series of this binomial power, negative 2, choose n. So this is combinatorics language that I'm using when I say choose, but these are the binomial coefficients. I'll write down what they equal in a moment, times u to the power n, right? So that's exactly what we want. And this converges for u, magnitude of u less than 1, is radius of convergence of 1. All right, so that means when it converges when capital D is at least as large as lowercase d. All right, and again, our question is asked, at least stated in the notes, it's stated more clearly, when capital D is very large, right? So when capital D is large, this is the idea, that this is about 1 over d cubed. So let's work this out. Let's remember that the binomial coefficients here, if we make this, say, an r, like we did in the notes, r choose n, this is equal to r times r minus 1 times r minus 2, all the way down to r minus n plus 1, all divided by n factorial. Okay, and I would like to make a formula for this that's easier for us to deal with, and so I'm going to look at these terms, okay, and make a table of these, all right? So, by the way, for us, r is negative 2, right? r is equal to negative 2 for us. So let's make a table in terms of n, though. So we want n equals 0, 1, 2, etc. By the way, when n is equal to 0, this coefficient is just equal to 1. Okay, it's just equal to 1. So this term, I'm going to call this, well, let's not give it a name because I don't want to have to give it a name. Let's just call it orange box, all right? So what's in this orange box? When n is 0, this is 1. When n is 1, this is just equal to negative 2. And then as n counts up, we have to start multiplying this by numbers equal to r minus 1, right? So take away, subtract 1, and then continue on. So the next term is going to be minus 2 times minus 3. And then when n is 3, we get minus 2 times minus 3 times minus 4. All right, and maybe we can already see the pattern, but let's just go one more. So when n is 4, we get -2 times -3 times -4. And I think we can see it. For a general formula, when n is just equal to n, what do we get? We get 1, 2, 3. We get n minus 1. This one then goes, I didn't write all this down, right? I'm jumping the gun. This one goes out one more term to -5. All right, so now what do we have? We have 1, 2, 3, 4. So we have n negative 1s, so -1 to the n. It's going to make it alternating. And then we have 2 times 3 times 4. We have n plus 1 factorial, right? And so we've got, you don't need the 1 here, but you can multiply all these by 1, and you have n plus 1 factorial for all these terms. And so what that tells us is that if we go back up here to our binomial coefficient, then -2 choose n is equal to the formula we've just worked out, which is -1 to the n times n plus 1 factorial, all divided by n factorial. We can't forget that n factorial, right? And this can then cancel, right? So this can cancel. This becomes -1 to the power n times n plus 1, and then the two factorials, n factorials, will cancel. And so there's our coefficients right there. And we can write down our binomial series in terms of these coefficients, right? So what we have is 1 plus u to the power -2 is equal to the sum. N goes from 0 to infinity. -1 to the n times n plus 1 times u to the n. And again, this converges. So that's exactly right. This converges for absolute value of u less than 1. All right, but remember, what we have is not just u. It's lowercase d over capital D, right? So we can plug this in and write 1 plus d over d squared. This is equal to the series. N goes from 0 to infinity. -1 to the n times n plus 1 times d over d to the power n. All right? This is a -2 power, though. And then let's write out the first few terms. So when n is 0, this all just comes out to be 1. All right? So when n is 0, this is 1. When n is 1, this is minus 2 times d over d. And then when n is 2, this is plus 3 times d squared over capital D squared. And then it just alternates back and forth, right? So 4 lowercase d cubed over capital D cubed plus minus, etc. All right, and so there's a power series expansion for this function right here. And what we want to do is go back and put this into this expression for the energy, right? And so what we learned then is our energy is q over d squared times this difference. So let's write this out. So we have our energy is q over capital D squared times 1 minus this, right? So let's be very careful how we write this down, but this power series that we just found is what goes right here. So minus 2d over d plus 3d squared over d squared minus 4d cubed over d cubed plus minus, etc. Right? And look what happens. When we actually do the subtraction, the electric field is charge q over d squared, capital D squared, times 1 minus 1. They're gone. 1 minus 1. Don't forget this minus, though, because this minus is going to change the signs of everything else, right? And so what's left in here is 2 times d over d minus 3d squared over d capital D squared plus 4 lowercase d cubed over capital D cubed minus plus, etc. All right, and finally what we get is that this is equal to 2 times q times d over d cubed. So that's constant, right? Q and lowercase d are constants. Capital D is allowed to change as the point moves away from the dipole. And then minus stuff that's all order, so we can use this notation. Order 1 over d squared. Oops, times d to the 4th, right? So as d gets very large, this term becomes negligible. And what we end up with in the result that we're looking for in the notes is that this electrical field is about, it's proportional to 1 over d cubed. So this numerator remains a constant. So I'm not ignoring it completely. That's what this symbol means. It's proportional to constant times 1 over d cubed when d is very large. Okay?